Underground mining industry observes huge losses in terms of human lives and infrastructure every year due to fatal fire hazards and blasts. We have visited a local coal mine called the Xing Ying Coal Mines in Wushan County in Chongqing, China. We discussed the safety monitoring issues with the administration of the coal company and interviewed one of the coal miner.
请问你叫啥子名字？你职业是啥子？
我叫周二全，我是煤矿工人。
请问你当煤矿工人好多年了
？15年。
请问在你工作的煤矿安全条件怎么样？
工作一般，偶尔发生火灾。
请问你和你同事的健康状况如何？
上班有时有点喘气。
那请问你在煤矿工作的那段时间内，有没有遇到啥子事故啊？
偶尔有遇到小火灾，没有大的那个。
请问现在煤矿内的安全监控状况如何呀？
我看到很多设计，有多个不是考虑生产的来源。
Based on our discussions, we have found that gas explosions and fire hazards are major causes of accidents in the Xing Ying coal mines. After some more research, we learned that gas explosions in coal mines is a global threat. Moreover, over the years, Chinese coal mines have seen the worst of the gas explosions. The gas explosions are caused by an inflammable gas called methane gas, and it is a natural byproduct of the coal extraction. Xing Ying coal mine has a methane monitoring system which triggers an alarm when the system senses a high concentration of methane. We have found that once a high concentration of methane is detected, the present monitoring system does not provide sufficient time to take necessary measures and it shuts down the power in the coal mine is immediately evacuated. We advocate a prediction-based monitoring system that can foresee a mishap ahead of time and takes necessary measures to prevent any loss of life or infrastructure without completely halting the mining work. There are two open challenges to build such a system. The first problem is how can we accurately predict long sequences of time series data? And the second problem is the wireless IoT data aggregation inside the coal mines is very highly ineffective due to high packet loss and latency. After some research, we have found that the long short-term memory encoder-decoder architecture can successfully learn data with long-term temporal dependencies and predict future sequences. This is a result of that shows an actual sensor reading in the predicted sensor reading that is generated using the LSTM encoder-decoder architecture. We have generated a blueprint of the coal mines with the help of the Coal Mine Administration. To demonstrate the efficacy of our approach, we have used 6 sensors to monitor methane gas accumulation and ventilation. The proposed system is designed as a fog server-enabled massive IoT sensor network that supports multi-hop cooperative communication. We have developed IoT sensor node and a gateway node for our testbed. Due to the high-stress underground environment, traditional multi-hop approaches such as clustered tree may not be suitable as single-point failure may jeopardize the whole network. The proposed system is based on tag data aggregation scheme that is a multi-path data delivery strategy where each node delivers the data to the gateway node while relaying through multiple partners. The node-to-node exchanges and the node-to-gateway exchanges follow MQTT along with TLS protocol. The gateway-to-fog server exchanges follows HTTP along with TLS protocol. We have developed a mini testbed to emulate the data aggregation scheme. We have deployed sensors inside this room. This is a typical wireless temperature and humidity sensor. We have deployed a gas sensor to monitor methane emissions. We have turned on the methane gas cylinder for the demonstration purpose. Now the sensor is reading the methane gas concentration. The Zigbee-based gateway module deployed near the entrance of the room aggregates all the IoT sensor network data and uploads the aggregated data to the fog server. We have also deployed other sensors in different locations inside the house as well to test the multipath propagation scheme. The laptop is working as a fog server and it receives the data through a Zigbee receiver module. The fog server stores the data in a database and fetches sequential data.